Officially, we do have office hours. Please say I updated it. Yeah. So Monday, Tuesday, Wednesday, Thursday, about 9:45 to 11:15. I plan to be there at 9:30. I'm always late, and so far this week too, I've been swamped with a bunch of administrative work that has been dragging me down even further. But yeah, my plan is to be there 9:45 to 11:15, right before class or right before your class, but then I also have a class Mondays and Wednesdays, the exact same time. I will also add Mondays and Thursdays. I don't have labs, so I could meet in the afternoon. You just need to let me know if that works or not. Okay, make sense? Okay. And then I will try to set up the virtual system. I forgot to do it today. Apologies if you tried. Theoretically, that works. Okay. This is actually an incredibly common question that pops up fairly frequently. And for not the reason that maybe for the reason that you did. But we'll see. It's in the Diels-Alder chapter. So when we're talking about homework, you should be using that as a guide to help kind of guide you through things. So if we're talking about Diels-Alder, more than likely, one step through this process is going to involve Diels-Alder, which means we can go through and look to see what's happening within it. Because we have work in here, I'm going to bet that this was how it was originally given to you, right? Okay. So if that's all the information we've got, we can look at our starting material and say, what do we see? Remember, keep in mind Diels-Alder. What is Diels-Alder? Okay. Diels-Alder, we take a diene, we react it with a dienophile to go through and make what?
Hexene?
A cyclohexene. Okay. Color coding roughly makes sense? Okay. So within that context, we should hopefully be able to see that our starting materials align pretty darn nicely with that system. Okay, so what we want to do is effectively copy that process across. Okay, so we could go through, draw our diene, and now I'm going to pick a different color and draw that green methyl group. Why am I going to call it a green color? Really, it can be any color. In this particular case, what I'm trying to reference it is that it's a hanger-on. Right? It's something on the core chemistry. So I want to focus on my core chemistry, and then I have to double back and address the things that are hanging on the structure. Okay? So I'm just going to hang it on down there. Okay? If I draw in the next molecule, my dienophile, I should immediately encounter a potential issue. That isn't, and for that matter, the diene is also asymmetric. They are both asymmetric molecules, so I could have had it align that way, or I could align it this direction. Is that going to change the end product?
No. You're working with p orbitals, so above or below doesn't matter.
So above or below, p orbitals, cycle around, the product that I would get. There's my cyclohexene. I draw my hangers on with where they were originally located. There's that hanger on. I meant to show it in green. There's that hanger on. And in the other case, we would get the exact same result, right? There's the green hanging on. Red. Are these two products identical? What's that?
They are connections?
No. Okay, so this pushes back. If we're referencing chapters, our textbook is probably chapter 5 or 6 would be my guess. What we're looking at is typically our chirality chapter, introducing that concept. So referencing enantiomers isn't a bad idea. I would step away from that initially and call them, okay, what's their relation? Are they identical or are they different? Because we have a claim that they were going to be identical. Are they identical? No. They also aren't technically different because they have the same molecular formula. Okay, so now you could have to go through and refine what is their absolute relationship. Arguably, that exact relationship is OChem 1 content. So that's not a big deal for us to identify now. However, remember our final is cumulative. It's supposed to cover the entire year. Being able to recognize that difference is something that's going to be important, and you should be able to identify it. Not going to show up a whole lot this semester, but kicking back through OChem 1 terms isn't a bad idea. Okay? For them to be enantiomers, they have to have the same connectivity. Okay? That connectivity can be defined any way you really want. For me, because we started with the diene and that first methyl group as a hanger-on, that's where I'm going to start as my position 1. I'm going to count arbitrarily, it doesn't really matter. Counterclockwise, 2, 3, 4 is where I see my carbonyl. If I look the other direction, counting the same way, 1, 2, okay, which means the carbonyl is connected at a different spot. This is different connectivities, which means these are disastomers or diastereomers are same connectivity, different orientation in space. Constitutional or structural isomers, okay, which is going to bring up kind of the larger point. Right away, they weren't identical. That becomes our primary thing that we have to be aware of. Okay? Why is that important? It matters which way these things react. Do I have the top result or do I get the bottom result? How do I know?
You would have to run the reaction.
I did run the reaction. So if your argument is I need to go to the lab to run it, that isn't a bad idea. And in the grand scheme, that is how we would discover this. Okay? And we would say, oh, it runs this way. Then we report out to the scientific literature saying this is how the reaction works, which then means everybody then running this experiment would verify, yes, that is indeed how it works, which then means anybody learning the content now needs to say, this is how it works. You don't get the privilege of now going to the lab to test it. You have to know. Okay? So how do we decide how it works?
Stability
Stability of what?
of each of the products, which ones were stable.
Okay? So we could try and jump to stability of the products. First off, that's going to be a challenge because there isn't a huge difference there. You might make an argument, oh, they're sterically closer. They aren't that close, so that's going to be pretty far off. The next part behind that is that if we're looking at an energy diagram, and if we're talking about the stability of the products, that becomes problematic when predicting our reaction. Because the reaction is dependent on this first part.
Oh, stability.
So the stability of the product doesn't help us. We could say stability of the intermediates, and intermediates is unfortunately also going to bite us in the butt because that's not an intermediate there. What is that? That's the activation complex. We never actually draw that. Okay? That's what's happening as these molecules get close enough to each other and the orbitals start to overlap and transition. And that means we'd have to draw molecular orbitals and all that fun stuff. Do you want to do that? God, I hope there's an easier way.
Is it based on cis and trans?
Nope. Endo and exo is actually a conversation. I didn't even start with this reaction. So to the point someone said that you get two products, this is not the two. When we talk about Diels-Alder producing two products, these are not the two products we're talking about. The two products we're talking about is that each of these has a chiral atom. And because we're looking at p orbitals, we can get above, below. We get two products with that being wedged or dashed. Okay? So it's not a endo-exo, it's not a two-product thing. There's another issue going on here. We're talking about the orientation of that starting material. How does it orient with this particular molecule? Does it align with the carbonyl aimed upwards or far away from the methyl, or does it aim closer to the methyl?
Does it want to aim away?
Why?
Steric hindrance, maybe?
So the steric hindrance. So again, we'll talk about the steric hindrance. What's our steric hindrance issue?
You know, more electrons close
There
to electrons.
isn't much of a difference.
Really?
Yep.
Huh.
They're not very close together. It's
They're
like
not- yeah,
they're
that's
both
true.
on the opposite side of the molecule.
Yeah.
So would we see the products?
Nope. You only get one.
We would only get one of the products, not
Mhm.
both. Well, does one of them have a lower activation energy?
Yeah. But how do we figure out what that lower activation energy is based off of? Okay. So let's double back, because there's a lot of stuff drawn up there. So assuming you're all okay with it, we're going to delete all those. And so if you wanted to go back and look and review what those structures were, we could go back and do that. But now what we'll do is focus primarily on kind of our answer, if you will. Trying to decide how I want to draw it. I think we're just going to do it this way, whether I'm happy with it or not. So what we're trying to understand, we talked about stability. So one of the things we could address with stability is reactivity. When we look at those two molecules, do we see anything in particular that jumps out that you might say, reactivity? So now step away from, yes, Diels-Alder and just say, okay, what do I see as reactive? Oxygen. How is oxygen reactive?
It's got electrons all around it.
True.
It's electronegative.
It's electronegative. If it's electronegative, what is it doing?
It's taking electrons.
Taking electrons from where?
What it's bonded to?
Awesome. What it's bonded to. What was it bonded to?
Carbon.
So we could go through and we could do this.
Oh, resonance then, I suppose.
Okay. And if we did that resonance, what does that do for us?
Gives us a very reactive oxygen and gives us heterocharges, or however you want to put that.
Sure. We got multiple charges, yeah. What reaction was this supposed to run?
Diels-Alder.
Our Diels-Alder. We've generated charges, great. Did those charges change any aspect of what made it Diels-Alder?
No,
Okay, what does that mean?
means nothing.
Means you're not done. How do those charges affect the Diels-Alder reaction? Are those charges directly going to affect the blue structure? No, why not?
They're not attached to the blue structure.
Cool. So instead of looking at how they affect the blue structure, let's see how they affect the red structure. Could I continue to do more resonance? I have another pi bond. What if that pi bond moved? Okay. Then that hanger-on that we had, yes, loses that positive charge. You're absolutely correct. I don't care necessarily. What else? You're making a funny face. Why?
What do you mean?
Okay, never mind.
I mean, you gotta write down the charges, I suppose.
We moved those electrons, but we didn't address the charges. The oxygen should be negatively charged, right? What else now?
Then you have primary.
I would have a positive charge down there on that carbon. Just because you said primary carbocation, and I do want to talk about that, is that a primary carbocation?
It's primary plus resonance.
It's primary plus resonance. So if anybody's like, primary carbocation, we can't do that. It's not a primary carbocation, it's primary plus resonance. Okay? Have we now shown how the hanger-on, our green group, could affect the chemistry of the Diels-Alder reaction?
Yes.
Yes, we're now actually showing that our dienophile is actually missing electrons, and it's missing electrons very particularly at one of the carbons of the dienophile. Okay? So what do I want to get to that carbon?
Electrons.
Cool. So now what I'm going to do is erase all those because I don't care about those anymore. Okay? And since I now know that that needs to have electrons, what do I have to find in my diene? Electrons. And in particular, where do I want to see those electrons? There's 2 spots, and since we haven't numbered them, let's see what you come up with. We'll sort of accept above and below. Okay, I would probably like top and bottom. Okay. Officially, we'd be looking at carbons 1 or 4 if we're doing our nomenclature system. Which one of those carbons is more likely to have electrons? Or are they equally likely? Why are they not equally likely? I'll come back to you.
You have that methyl to worry about.
Cool.
Change.
The molecule is asymmetric. That methyl group is going to have an effect that affects 1 or 4 preferentially. Ivan?
I was just going to say, because one is like sticking out, and like four is more like inside molecule kind of.
No, sorry.
Well, I mean, with the methyl, couldn't that theoretically impede things from getting to the pi bond, or at least the p orbitals?
What's reacting when we run the Diels-Alder reaction?
The p orbital,
The p orbital located on where?
carbon 1,
Carbon 1. Where is the methyl group?
somewhere else.
Carbon 2. Okay, so it's 1 atom further away. And then is it in the up-down place of where the p orbital is? This goes all the way back to OChem 1 or even GenChem 1, talking about shapes of the molecules. These are all trigonal planar, which means the bonds are all in the plane of the paper, and the p orbital that's reacting is coming where? In and out of the plane of the paper, which means that methyl group is not doing anything sterically to affect this reaction.
I mean, with that methyl there, you'd be able to make a more stable carbocation, meaning that you'd have a more stable product. if-
Oh. So what you're suggesting is that if we did this, we would build a negative charge at carbon 1. We wanted to see a negative charge, but we would also build a carbocation at position 2. And if we did that resonance with the top carbon, we'd be looking at a secondary carbocation versus secondary, except it's not secondary on the bottom, it's tertiary because there's an extra methyl group. And yes, officially plus resonance. So we're looking at a tertiary plus resonance versus a secondary plus resonance. Which one's more stable? Which means this is our reactive state. Which means when I go through to run the Diels-Alder reaction, I need to make sure this negative hooks up with that positive. Conveniently drawn in the proper orientation, which means the only product that we should get out of this, recording, don't know when I did that. Red. What do we say? There's purple, there's purple. There's our green hanging on. There's our double bond there. That's the only product we get. Anybody upset that we don't see the blue carbocation? Not quite sure I believe you. Anybody upset that you don't see the green structure with the negative charge on the oxygen? Why is it a double bond now? The resonance structures that we drew helped predict where the chemistry was located so that we could complete the reaction and we knew the orientation. Okay? Those resonance structures, we could push all the arrows and show where everything went and bounced and all of that. It would be a lot of arrow pushing and it would be very confusing to see. Ultimately, the chemistry is still happening up here. The resonance is telling us where that chemistry needs to happen. The resonance tells us that when we do our arrow pushing, with our starting, whoops, that's not a hydrogen, it's carbon, that our arrow needs to go here to here to here. The resonance gave us that information. What we're doing is just acknowledging that and now effectively moving away from the resonance, because the resonance is just how the electrons move around. It's not the formal reaction process. Kind of, sort of? What does that mean we just produced? 1/3 of our problem. Yay. Okay. Big reveal. Okay. We have to get that proper alignment of those pieces. This is where this chemistry can become challenging. Okay? So if we modify this, come on. There we go. That should be our first box. Okay? We've now done Diels-Alder. So I can erase it. Can I erase everything? Well, almost everything. So we would now move to step 2. Okay? Step 2, we now look at the next system we've got. Okay? Based off of our first product, could that do Diels-Alder?
No.
It's a weird statement. Yeah, it could.
Could it?
Because it would be the dienophile. It can't be the diene. Okay? So this could still do Diels-Alder, but given the reagent that we've got, no diene, are we talking about a Diels-Alder reaction?
No.
Nope. Okay, so that's out of play. We don't have to worry about Diels-Alder anymore. Thank God we don't have to worry about all that spatial stuff. Thankfully, we didn't have to worry about stereochemistry and all that. I'll double check on that in a second. Okay, but now we've got this weird reagent, CH3Li. Invariably, every semester, people go, but you've never showed me what that reagent is. There's no way I could figure this out. And every semester, I call bullshit. Should never record that. Okay? Because when we talk about chemistry, it's not reagents, it's look for the chemistry. So when you see CH3Li, what do you see?
A metal and a non-metal?
Okay. Heard lots of answers shouted out. Admittedly, I didn't hear what yours was, Josie. You just said CH3. Okay. CH3, we'll walk through all of these. I just see a CH3. Well, what is that CH3? Is it a positive or a negative? Because that's really different chemistries. Okay. I heard leaving group. Sorry, I forgot it already. Okay, what is leaving group? Something has to leave and take electrons with it. What would be your standard leaving groups? What's something that you go, leaving group, that thing is a leaving group.
Bromine.
Bromine are halogens. Okay, so large electronegative elements. Do you see large electronegative elements? No. You run into a little bit of gray area because you can almost always call something a leaving group, but I would say no, we don't have a good standout for a leaving group. To the methyl group, or CH3, sorry, you said CH3, we still haven't defined how it would react, so that's not going to work very well. But then I heard a different statement, which I would say goes all the way back to the beginning, which is exactly what I want you to do. You see lithium, which is on the left-hand side of the periodic table, so it's a metal, connected to, hopefully you see that it's kind of just a carbon, which is the right-hand side of the periodic table. You've got a metal and a non-metal. You have what type of bond? An ionic bond. So let's look at that structure. In that ionic bond, where do the electrons prefer to be? With the carbon. Why did you go, because you looked at it and you're like, ooh, I don't want to say that.
Well, because metals, they have a positive charge, and it's like...
Absolutely. Metals will always be positive. But that was your just the metals?
And carbon's not very electronegative?
Bingo, that's probably the thing that you really stuck you, is that we're saying those electrons belong on the carbon, which means when we look at that structure, what we're looking at is, yes, a CH3, but more importantly, a CH3 negative. And you may go, I don't want to do that. I don't give a flying rat what you care about. That's the reagent. That's what it is. You do what it is. Okay? At least that's your starting point. If you get it wrong, then you're going to be like, well, maybe there was something wrong within my assumptions, and you can try and backtrack through. Okay? But 80% of the time, 90% of the time, you fall back on your principles, it will work. Okay? I would argue 80 to 90% of the time, you don't fall back on your principles and you fall back on trying to memorize. That's where it becomes problematic. Okay? So I have a negative carbon. What do I need to stabilize that negative carbon? Positive. So what do I have to do? Find a positive in this molecule.
There's 2 places.
Okay? I'm here in 2 places. Of course, I beg to differ, but go ahead.
Oh.
What are the 2 places?
Well, when looking at the double bonded oxygen, you can move the electrons onto the oxygen, creating a negative oxygen and a positive, I mean just a carbocation. And then at the other double bond, you can move the electrons to the upper carbon because that would make a more stable carbocation. So there's 2.
Okay. What is the difference about those 2 pi bonds that you've referenced? There's really huge difference.
One has an oxygen.
One is bound into the oxygen. What does that change about the chemistry of that bond? What kind of bond is the carbon-carbon one? What kind of bond is the carbon-oxygen one?
Oh, where's my brain not working right now?
What's that?
Non-polar and polar?
Non-polar covalent and polar covalent. Which is more reactive? Polar covalent. I could care less about you drawing resonance for the alkene. The alkene's not going to be your source of chemistry when I have that other positive sitting there. So what do I need to do? I will take my negative and I will react it with my positive. That would necessarily break the octet, which is why I need to have that red arrow happen also. Okay? This is where smart work goofed. And we'll address it here in a second. It's the one reason why I don't like this question. If we look at our changes, we've got our oxygen now with 3 lone pairs. We could draw that hydrogen if we really wanted to. And then we've got our CH3 down here. An oxygen with 3 lone pairs would be negatively charged. That would be bad. We would need to neutralize it. Okay? So let's double back to this reagent CH3Li. Okay, you didn't like it. Why'd you not like it?
But, me?
Yeah. You said you didn't like it.
Oh, because carbon's are very electronegative.
Carbon's not electronegative, can't stabilize that negative charge. Well, we don't like seeing that. Okay? And you're right, it is insanely reactive. Metal-carbon bonds are their own special class of chemistry we will talk about later in the semester. Okay? They are insanely reactive. Okay? They are also insanely powerful. The vast majority of this semester is spent on trying to identify and find negative carbons. They're very, very, very important class of compounds because without negative carbons, we can't make larger carbon structures. All we can do is change functional groups on an individual carbon. A negative carbon allows us to make a larger structure. That's powerful. Okay? They are so reactive that if we're going to run this reaction, it's going to create charged intermediates. We need to neutralize those charged intermediates. Okay? We also need to potentially neutralize any unreacted negative carbons. What would be the easiest thing that we could put into solution to neutralize those negatives?
Well, it says on here H3O+.
Oh, I forgot. That's why I'm okay with it. Okay? And I think what happened is I complained about the question. And they realized that it was too hard to edit the reaction, and so they just added text. The text says that this happens in 2 steps. You do the CH3Li followed by H3O+. And H3O+ is supplying positive hydrogens. Okay? So what happens is that we would replace one of those lone pairs with a bond to a hydrogen. Okay? And again, I'm not positive, but yeah, if you read the footnotes, they're like, and do this. Just a bit obnoxious because nobody reads footnotes.
Just out of curiosity, this might be a dumb question, but why would it not react with the lithium from then on?
The lithium, so if the lithium connected with the oxygen, what kind of bond did you make?
Oh, you said the same problem before.
Yeah. Okay. It's more stable. It's more stable than the carbon lithium, which is one of the reasons why it drives to make the product. Okay, but it is still very reactive, and you need to neutralize that formally by making it a polar covalent bond as opposed to an ionic bond. All right? Cool. I'm not going to erase that structure to see what you put underneath just because we already knew there was a mistake in box 1. So now what happens? We move on to MCPBA. What is MCPBA?
No clue.
Okay. This is one that I would push, as a memorization. Okay. It will show up frequently enough that knowing it is probably better than trying to understand the whole chemistry behind it. And for sure, you're not going to be able to pick out MCPBA and say, oh, that means it's metachloroperoxybenzoic acid. Okay? Or that MCPBA means, can I erase stuff? Or that it means that structure. That's a Cl at the bottom. Okay. So I would argue you just memorize what MCPBA does. Anybody have any vague itches in the back of their mind what MCPBA did? Okay. Depending on how much you've been reviewing across the summer, I would argue this is something that very quickly fell out during the summer because it was right at the tail end of at least my OChem one. Okay. By the end of this week, you hit a review video again that's going to push some of these reagents, and you should know it. MCPBA reacts with alkenes to make epoxides. Do you know what an alkene is? Don't laugh. That's a question. Do you know what an alkene is? You laugh, but then you're all silent.
Isn't it just double carbon?
Pi bond isn't quite good enough. It's a good step.
Carbon-to-carbon double bond.
Carbon-to-carbon double bond or carbon-to-carbon pi and sigma bond. Cool. What MCPBA is reacting with is the carbon-to-carbon pi bond. So I like the reference to pi bond better. And it makes the epoxide. What's an epoxide?
It's another one that's like the pi bond's like bonded to an oxygen.
You're describing the mechanism, which I like. That's good. Yeah, that's a little better. Okay, just getting to the final kind of nitty-gritty of the detail. Oh, and all. It's a 3-membered ring with the oxygen in it. And we now have a final answer. We don't have to be explicit with the CH3 or that hydrogen anymore. Okay, if you are going to add the hydrogen, never mind. You can add that hydrogen if you want. Okay. Do we see any potential complications of this final answer?
There's no lone pairs on the oxygen 3-member ring.
Okay. That's a mistake on my part. I would argue not the complication I'm fishing for. Is there a complication within this final structure? Do better. There's not a chiral center. Do better. There's 4 chiral centers within this. That's lots of wedges and dashes to be aware of and process as you move through this. Okay, that could be a very painful thing to have to go through and process. Could you do that? Not for a single answer, but for 4. I think this would come out to 4 different products. I'd have to look at that a little bit more carefully, but I think it would come out to 4 different products. So you could draw 4 different structures. So not all possible, because if I have 4, it's 2 to the 4th. What's 2 to the 4th? 16? Okay. It's not 16 possible answers. Okay, there's only 4. Okay. That's going to be dependent on the mechanism behind each of those steps along the way. Okay, so when you do the Diels-Alder, that's how we formed. Okay, that was step 1. This was step 2. Both of these were step 3. So understanding the stereochemistry at each of those spots has to do with understanding how each of those things reacted. So if we move to the final may be cumulative, you may be all multiple choice. You go, oh, I don't have to draw mechanisms. That doesn't mean you're not responsible for mechanisms. The way they get you responsible for mechanisms is they add stereo centers into their reaction, okay, into their answer choices. As soon as you have stereo centers, pretty much the only way you can predict what they are is based off of understanding a mechanism. Or lots and lots and lots of memorization. Okay? Because there are 4 possible ways, I'm going to go way out on a limb here. It's actually not that far of a limb. And say there's no way in hell SmartWork wanted you to actually draw any one of those possible 4 because it's way too complex. And if we jump to our solution, they don't show the stereo centers. You'll note they do show the hydrogen. You don't have to. If it complains, that's something you send me an email about and I'll fix. Where?
No.
So, careful. Solution versus failed attempt. So you gotta be careful. Okay? We good? Cool. 12:45. Let's take a hot break. To the boards. Okay, real quickly, you're gonna get a picture here
Understand front,
from camera. Whoop.
holy, whatever else. Yeah.
Use photo, there it is. Okay, so what you see roughly, students were given this, and the first question was find the intermediate, then find another intermediate, and then find another intermediate, and find another intermediate. That's where we're getting those, and then finally getting to the products, and then evaluating what's going on with those individual products. That's all you get in a recording. Good luck.
Wish you could talk that way in the recorded lectures, like the video.
Have I told you about what happened with the recorded lectures?
No.
Yeah, here's what happened with the recorded lectures. Students complained in class, you talk too fast. It's like, okay. When I went to record the lectures, I was like, I intentionally slowed myself down to not talk so fast.
Kind of funny because I watch all of them on 1.5 speed.
Yeah. That's how I rewatch them. I'm like, I need double time on this. Is ridiculous. Don't worry, you're not in it. Officially, I am recording, though. This question was, oh my God. This question was, take a look at those two and find reactivity is, I think, where it started. Then people drew resonance. Whoops. And people drew resonance, and then it was try and predict the product. That predict the product was attempted down here, and as you might see in comparison to the actual product, missed some pieces. Deals Alder's very complex. You need to go through a number and try and keep sense of where all those pieces are moving as you navigate stuff. Big deal, write stuff down, talk about it. Now we're done with the lecture.